Okay, so in the last video we discussed the concept of stress, right? And that was the way that we defined stress was that it was the wait 1 second. Okay, yeah. Let me restart. So in the last video we discussed the idea of stress, the amount of force experienced on an object divided by its cross-sectional area, right? The way that it worked was that it's an idea of how much force or load they're applying without considering the area as well, or accounting for that as well. So that way you're only worrying about the material and nothing else. Yeah, not the dimensions of the object. Next up, we are talking about strain, which sounds like a very similar concept to stress, but it's actually a little different. The idea of strain comes from the amount of extension an object has. Say if I have two rubber bands, or like two rubber strings. So imagine you got a rubber band and you like snipped it. And if I have one that's, say that they're the same like cross-sectional area, my drawing isn't exactly great, but you apply the same amount of force or the same stress in it, right? So I apply an amount of stress here across, and I apply the same stress across. Yeah, so same force, same area, same stress. You'd still expect this second one to extend much longer. So imagine this stress produces a change in dimensions. Yeah. Small change in dimensions for a smaller length, a large change in dimensions for a larger length. So what I'm saying is that this delta L and this delta L. Delta is usually given for change and L is for length. So this change in length is much bigger compared to that change in length. But the thing that stays constant with this material is that if you get the original length, obviously these original lengths won't stay the same. But for the same stress, for the same stress, what you're going to experience is that the ratio between this change in length divided by the original length, that's going to stay the same. And we give this the term strain. The strain is just given by the letter epsilon here. So it's simple as that, that the change in length divided by original length that is what we define as our strain. Now, you notice that because these are both length units, strain is given as just a number. There's no units for this. They cancel out. So strain generally is given by a decimal, but you can go and give it a fraction as well. Or, not a fraction, a percentage. Yeah. Now, building on from this, what we notice is that for relatively small, up to a point, for materials, for a given amount of stress, the strain experience is proportional to it. So what I'm saying is that at least for like pretty small stresses, small in the scale of materials, so it's like a few thousand pascals or so, at least, up to a few million actually, but a few thousand pascals at least, you'll experience a sort of linear trend. They're proportional to one another, stress and strain. Yeah. This is the idea called Hooke's law. Just to get that name down, but don't exactly have to memorize that. And literally what this guy says is that the amount of force required to deform or extend something is proportional to the amount that you're extending it. Hooke's law is often applied to springs. Doing like a little spring across. Yeah. And if you apply like a given force, you'll expect it to have a given change in position. And so what that law itself says is that the force is proportional. Got that symbol. Proportional to that change in length. Likewise, here, when we put it into the context of materials, you end up saying that your stress is proportional to your strain. At least up to a certain limit, yeah. And that certain limit we'll get to a little bit later. So the way that we can also say this is that I can say that stress is equal to E times a certain constant. That's what it means for them to be proportional. Now in this case, the constant that we call is E, and this constant itself has an important property in the context of material science. This constant, let me change colors, this constant is what we call Young's modulus. Young's modulus. The other name for this, because things get called by many names, is also known as, I'll just call it AKA, modulus, I'll just call it mod, of elasticity. And this seems like a better name for this, because it is a measure of how elastic some things are. If you compare this material, the material that has a slope of this, whatever that is, depending on the units, and you want to compare it to something with a slope of this, the slope is given by this E. So it's like y equals mx. This is like your y, this is like your m. So y equals m. Y, so this is like y, this is like x, so this is like your m. Yeah, so it's like the slope of the graph. So this E part, it shows the slope of the graph, yeah. So now what that means in like a visual sense is that it requires a smaller amount of force to extend it by a larger amount. And that literally is what elasticity, in some sense, how elastic something is like how you interpret it in real life. You know, if you compare like a metal bar and a rubber band, right? Imagine my little metal bar and my yellow rubber band, right? Applying the same stress or force, applying the same stress or force, it'll only change the length by like a tiny amount for a metal string bar thing. Whereas for the same amount of force, you're going to experience a significantly larger change in length. And that's what this slope of this graph of this Young's modulus or modulus of elasticity tells you. How much stress or force does it require to extend it or strain the object?